Alright, this is 2-3 in Advanced Algebra 2, and today we get introduced to piecewise linear functions. They call it piecewise because the graph's going to be in different pieces, and linear because those pieces will be straight lines, or really in this case they'll be little segments. Next time we'll do some with rays and segments, but today nothing but little segments because we're going to graph a step function. It's called a step function because when we graph it, it'll look like little steps, like in a staircase, and they'll be made up of segments. So let's just get to a real-life example here and see what's going on. So our example is we're going to mail a first-class letter. So we're going to go to the post office, we're going to mail a letter, and here's the price. If the letter itself weighs 1 ounce or less, it's going to cost us 49 cents to mail that letter. But the postage paid for anything will jump by 21 cents for every ounce after that. So let's just kind of fill out this table. So here in the X column we've got the weight of our letter in ounces, and then in the Y column we've got the postage, like how much we're going to pay in cents. So it says if X is our weight, if that letter weighs greater than 0 ounces, because obviously if it weighs nothing we're not going to mail anything, but if it weighs greater than 0 but less than or equal to 1 ounce, they want to know what the postage is. Well, they say that's going to cost us 49 cents. And since this is in cents, we're not going to put 0.49 because that's in dollars, right? So it's 49 total cents right here. So this letter, if it's greater than 0 ounces or less than or equal to 1 ounce, it's going to be 49 cents. Now, if it's going to weigh more than an ounce, but less than or equal to 2 ounces, we've got to add 21 cents to that. So notice here that 1 does not count in this because if it weighed 1 ounce, we were still up in this category. So if I take the 49 cents and add 21 cents to it, that's going to give us a total of 70 cents. So even if, this thing weighed 1.1 ounces, we had to pay that additional 21 cents because it weighed more than 1 ounce. So then again, if we have our letter and it's weighing 1.3 ounces, 1.7 ounces, all the way up to 2 ounces, it's only going to cost us 70 cents to mail that. But as soon as we get bigger than 2 ounces, like even 2.00001 ounces, we've got to add an additional 21 cents, so that would get us into the 91 cents, all the way up to 3 ounces, and including 3. And then for the next ounce above that, we add another 21 cents. So that would give us 91 plus 21, which is, of course, 112. Now, we're not going to put 1.12 because that's in dollars again. It's 112 cents. Yes, that's $1.12, but we're in cents, so we don't do that decimal deal. And this pattern would continue, basically. So that's just a little table of values. Let's write a function. So the function will be f of x equals, and now here's the new part. We've got all these different pieces right here. And according to our table, we're only going to put these 4 pieces in. We're going to start with this cool bracket right here, saying all of these little pieces are a part of this function. So our function will equal 49 cents if, so here's the restraints on our domain, the restrictions in the domain. If x is basically, we're just going to take this part of our table and put it over here. If x is greater than 0, but at the same time less than or equal to 1, that's totally what the price of our stamp would be, or our postage would be 49 cents. Then we rock and roll it down here. It would be 70 cents if the weight of our letter is greater than 1 ounce, but less than or equal to 2 ounces. And then we do it again. It's basically like putting this table over here in this function form. It'd be 91 cents if our postage is greater than 2 ounces. I should say our weight is greater than 2 ounces or less than or equal to 3. And then finally, the function would equal 112. Basically, y equals 112 if our postage is greater than 3 ounces and less than or equal to 4. And this pattern will continue, ... It's not like this is the end of it, but we're just going to kind of stop here. We're just going to write our table in this form. And now let's actually kind of graph this situation right here. So the first thing you need on any good graph is a title. So like, what is this situation talking about? It's talking about the cost of a first-class letter. So I'll have you write that up there. And if I'm moving too fast, you can always pause the video to get that written down. And then we'll label our two axes. X, we've already kind of figured that out right here, is the weight in ounces. And notice I don't really want to list every single one of these little marks right here. It's like I'd get up to 14. It's like I don't need that. It's like I'm just going to go every other one. So just kind of spacing it out a little bit. And Y, of course, is the postage in cents. So again, please pause the video, get all that written down, and then we'll label our Y scale. That's kind of the more challenging part. So here's the thing on the Y scale. It's like you don't want to go counting by your normals, you know, like counting by fives or counting by tens or anything like that. Why don't we just count by what makes sense? Like, isn't really everything increasing by 21 cents? You know, this went up by 21, then up by 21, then up by 21. So we're going to kind of go up by 21. It's weird to count that way, but that's what we're going to do. But the other goofy part is, it's like we didn't start at 0, we started at 49. So I'm totally going to like break this scale off. That's what this squiggle mark is right here. It's like I'm going to break the scale and say, dude, I started at 49 cents, you know, and then I just kind of spaced it out every other one. I counted up by 21s. So there's your 70, there's your 91, 112, and then even though our table didn't go past that, we're going to continue our scale up until we run out of space. So I'll let you do that. Just break the scale and say, yeah, we're starting at 49. Get up to 70, and etc. So pause the video and get that made, and then we'll actually make the step graph ourselves. So here's our step function that we're going to make right here. The step function, again, is going to be made up of those segments. It's just kind of something you got to see until we get good at. So basically, if the weight of our letter was 0, meaning we had nothing, we wouldn't pay anything, so we've got ourselves an open dot right here, meaning this doesn't count. But man, if we had a letter and it weighed anything more than that, like even 0.01 ounces, it's going to cost us 49 cents all the way up until it weighed 1 ounce, which still counted. That's what that equal to bar is right here in our domain. It's like the entire weight of anything, be it a half ounce, 3/4 of an ounce, all the way up to 1 ounce, the price is going to be 49 cents. So that's this nice horizontal segment that we're making right here. We basically just graphed y equals 49. If you go back to your Algebra 1 days, this is the function. This is a horizontal line right here because there's no x's in it. It's only got one variable. It's y equals 49. But we restricted the domain to be, it's got to be bigger than 0, so that's why that doesn't count, and at the same time less than or equal to 1. So everything in there works. Then, when we graph our next piece, the domain is going to be between 1 and 2, where 1 doesn't count, but 2 does count. But the price is actually y equals 70 in that situation. That's our postage. So 1 does not count, and 2 does count. So we'll put ourselves a closed dot, and we'll make this segment. And notice this is a function still, because this guy's passing the vertical line test. Like if I put a vertical line between here, it would only go through the function in one spot, because that's an open dot and that's a closed dot. Then we graph this function. The domain is between 2 and 3. Right, so we're only graphing from 2 to 3. 2 does not count in this situation, but 3 does count. That's where we got ourselves an open dot here at 2 and a closed dot at 3. And everything in between there counts. So like if the letter weighed 2.6 ounces, you know, it would cost us 91 cents. If it weighed 2.1 ounces, it would cost us 91 cents. If it weighed 2.99 ounces, it would cost us 91 cents. Like every single possible weight between 2, not included, and 3 included, our postage would cost us 91 cents. And then etc. for the between 3 and 4, where 3 does not count, so open dot, and 4 does count, closed dot. And then this pattern is going to continue even though we ran out of our table. If we went between 4 and 5 cents, so it would cost us 133. That's why we counted by the 21s. And then between 5 and 6 would cost us 154 cents. and then if it was between 6 ounces and 7 ounces, where 6 doesn't count but 7 does, like this. And then we're going to put this dot, 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 and an arrow saying, hey man, this little pattern continues right here. So it's like these steps. This is why this is called a step graph, because if you look at the graph, they look like steps. He's still a function, because again, if I did the vertical line test, if I drew a beautiful little vertical line right here, it's like it only crossed that guy in one place. It only touched that dude in one place. Well, that didn't graph very well, but I think you get the idea. Even if you went through at this cool place of 2, if I could actually get that to happen here, it's like it only touches the graph there in one place, here at this closed dot, not at that open dot. So this is a function. So now let's evaluate it. Part B says find f of 1.3. So you know you do f of x, so f of x, they're saying like x is 1.3 in this situation. That's the price of an envelope that weighs 1.3 ounces. Well, 1.3 out of all of these little domains here, he's not in this guy, right, because 1.3 is bigger. 1.3 is between 1 and 2, or we could read our graph. F of 1.3 would be on this blue step right here. That's going to be 70 cents. So it says find the function evaluated at 2.99. That is the price of an envelope that weighs 2.99 ounces. So you go to 2.99, which is between 2 and 3, and boom, that's going to be 91 cents. So that's the basic idea of a step function. Let's try another one right here. Dave created an app that's a knockoff of Uber. When you use his app, he'll come pick you up and give you a ride to whatever destination you desire. His app will charge you $1.50 for him to pick you up, and then for every whole mile you drive, you'll be charged 20 cents per mile. Let's fill out the table here. So I've already kind of got the X and the Y things labeled, like how many miles you have driven and what your fare is, like that's the price of what you pay him. It's called a fare if you ever ride in like a taxi or an Uber ride or anything like that. So if you have driven in Dave's little ride right here bigger than 0, because obviously you're going to go somewhere, right? He's not just going to call him and not take you anywhere. So if you're going to go more than 0 miles but less than or equal to 1, so that's going to cost you that $1.50 right there. So if you don't even go a mile, that's what this whole like startup charge is right here. That's the $1.50. But man, after you go that mile, he's going to charge you a little more, so 20 cents more per mile. So between 1 and 2 miles, where 1 doesn't count and 2 does count, it's going to cost you $1.70, right? Because you had to pay the $1.50 for him to come pick you up, and then an additional 20 cents. And then here's the next mile to where you go more than 2 miles but less than or equal to 3 miles. That's going to be another 20 cents, so $1.90. And then here, if you go more than 3 miles but less than or equal to 4 miles, it's going to cost you $2.10, and etc. That pattern continues. So you can see there's little steps. Every mile is going to cost you an extra 20 cents, so you're going to move, your price is going to move in steps. So f of x will equal, and then we're just going to put these here in a nice little function. The guy will equal $1.50 if x is bigger than 0 and at the same time less than or equal to 1. And then our next step will be, it's going to cost us $1.70 if my domain, if the miles we drove were greater than 1, right, more than a mile, but less than or equal to 2 miles, it's still going to cost us $1.70. And then it's going to cost us $1.90 if the miles that he gave us a ride was more than 2 miles, but less than or equal to 3 miles. And it's going to be $2.10 if the miles that we have traveled was more than 3, but less than or equal to 4. And then that pattern will continue. So dot, dot, dot. A couple dots in there. And now let's title our graph. So what do you think would be a good title for this? I'll give you a second to think about that. I think that it's about like the price of a ride from Dave. You know, anything that has to do with Dave and this ride. You know, there is no perfect title on this. And then x-axis label would be miles. We kind of have that figured out right here. And here's your y-axis label, basically. So miles. And again, I'll skip some spaces to kind of just spread this out a little bit. I don't really like to count by threes, like if you went like every 3 spaces. I like to do even numbers. I'm just kind of an even guy. So if you went by fours, it's really not that big of a deal. But going by ones would be really, you'd get up to 14, and that's just too many steps. So miles. And then our fare again is on the y-axis scale. And again, like I said, you can pause the video to figure this out. Notice how I broke the scale, started with my original cost of $1.50, and then the slope, basically your rate of change, is going up 20 cents every time, so I went every other one and went up by 20 cents. So get that video paused and get that scale made. Alright, and now let's put our steps. So obviously if we don't call Dave at all, and if we did nothing, we'd be charged nothing, so that's why this is an open dot. But man, if we called Dave, and even if he had to take us 1/10 of a mile or something like that, it's going to cost us $1.50. But anything from 0 all the way up to 1 mile is going to cost us $1.50. And then, man, if we went past that mile, even if it was 1.000000001 miles, it's like we had to pay that extra 20 cents, and that's going to cost us $1.70. So open dot on the left, closed dot on the right. Anything like that 1.0000001 is right here on this blue step right here. Then the next step, more than 2 miles, is going to cost us $1.90, but not 2 miles. 2 miles doesn't cost us $1.90. Exactly 2 miles cost us $1.70. So, but more than 2, all the way up to 3 included, is going to cost us this, and then just continue making your steps. It's linear, that's why it's that constant rate of change of going up 20 cents every time, right? 20 cents. Boom, closed, and then boom, closed, and boom, closed. And then that pattern continues, so you put the dot, dot, dot with an arrow. It's like that pattern continues right there. So let's find f of 3.7, meaning since this is x, it's like what would be the fare for a 3.7 mile ride? Well, we use our graph. 3.7 is between 3 and 4, and that would cost us $2.10. So you can put the dollar sign if you want to. You really don't have to, but find the fare of a 2-mile ride. So 2 is an interesting number because he's one of those boundary numbers. It's like here's where there's a 2 involved in the domain, and so is here. Where does the 2 count, though? It counts right here where you got the equal to bar. So a 2-mile ride would cost you exactly $1.70 because you didn't actually go over 2 miles. It was included in this original domain right here. Alright, and then finally, now here is a graph. Let's read it and kind of interpret it. It says the cost of weekend services by Eagle Cable is shown by this graph. So write a piecewise defined function that represents the cost for service during the first 5 hours as defined in the graph. So basically it's like, oh, you've got problems with your cable, somebody's got to come out to your house and fix it. What's the cost going to be right here? So this is like how many hours they're actually out on the job. And then this is the price that they're going to pay right here. So basically every step needs to be in our function. There's 3 steps, so we're going to do f of x equals, and then we'll put the cool little bracket. And now I need 3 steps. That's a horrible little bracket. Should only have one of those little dudes. So there's your set bracket. Each step. So what does this step represent? Well, the price is $120, right? So he's $120. If, and then you just kind of tell me the definition, where the domain is. So if x is always in the middle, these symbols always point to the left, my smaller boundary is basically 0, and he does not count, and it goes all the way up to 1, and 1 does count, so you'll need the equal to bar right there. So there's your 1. It's going to cost us $120 if they come out and they're there for an hour or less, right? If it's greater than 0 hours, so obviously they have to come out, but less than or equal to 1 hour. So anything that's 15 minutes, 30 minutes, 52 minutes, it costs us $120. Then the price jumped to $190 for them to come out if the time that they're out there is greater than 1 hour. So if they're there for more than an hour, but then less than or equal to 2 hours. And then we've got this interesting thing. Now look at this step. He's a longer step in this situation. They're going to charge us $260. So it did go up by the same amount. It was $70 for each additional hour. So it kind of had the same slope. It doesn't have to. It could have went up to a different price. It didn't have to go up by 70 here and up by 70 here. If X is greater than 2 hours, but then notice it went all the way up to 5 hours, so less than or equal to 5 hours. And that's all that they talk about. They could be there for longer than 5 hours. It's just not represented in this table right here. But man, you've got some major cable issues if they're at your house for more than 5 hours. So that's all they want was write this step function. Here's your domains. It's like where is the x values of all the steps right here, and this is the little y values right here on the step function.
The way that happens is it's called a step function, which you can kind of see over there by the pencil sharpener what it's going to look like. That's what a step function looks like. We call them round downs. They've got this fancy schmancy expression with like a double bracket inside of each other, like a double bracket, if you will. It means we're going to do round down. Also, this is the same symbol, just like weird little brackets that only have the bottoms. Where is the bracket at? At the top or at the bottom? Bottom means round it down, right? Take that number and round it down is all that it means. Round down. It's called greatest integer less than or equal to x, blah, 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 blah. In our own words, it's called rounded down. So let's just get practicing rounding stuff down in the first place. I drew a number line here. That will help us. If we take 3.2, which is in those round down brackets, correct? Round it down to the nearest integer. What does 3.2 round down to? 3. Pretty simple. Correct? 3.2 rounds down to 3. Awesome. 7.89. Round it down to the nearest integer. What does it round down to? 7. We've got this bad habit that says, well, isn't that over like 0.5, so don't you round it up? Well, of course, if they were just rounding, but this says round it down, correct? So it doesn't matter what it is. You round it down to 7. Negative 2.2. Slow down with the negatives. Here's negative 2. Here's negative 3. Isn't negative 2.2 like right about here? Let's use a different color. Isn't it about like right here? Round it down to the next integer. What does negative 2.2 round down to? Doesn't it need to go down? Aren't these getting smaller? Right? Round it down to negative 3. With me on that? Try the next one. Negative 6.77. Round it down. If you need to think of it as a number line, it would be like right here, negative 6.77. What would it round down to? Negative 7. Cool? These brackets, whatever kind of brackets they are, they're a grouping symbol. So we have to do what's in the grouping symbols first. It's order of operations. That's the first thing. We need to add those together. Grab yourself your calculator. Add those together for me. What is 1.52 plus 4.32? 5.83. And it's still in those round down brackets. Cool. What does 5.83 round down to? To 5. Finish. Finish. Simplify them if they need to be simplified. Pi, which is 3.14159, blah, 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 blah. What's it round down to? 3. And then this, you got to show me this. Cool? And that's an interesting one. Don't you get negative 4 once you simplify all that? Round it down to the nearest integer. What does negative 4, which is right here, let's go blue, which is right here, what does it round down to the nearest integer? What do you think? It is an integer. Would you agree with that? So the nearest integer it rounds down to is itself at negative 4. You don't take it down to negative 5. It's at negative 4. With me on that? Cool? Next, you've got all these instructions about the greatest integer or step function. It tells you the domain all the time will be all reals. The range, it's got a typo in it. They say the range is the set of all y such that y is an element of the real number system. That is wrong. Cross out that r, that double bar r, and put a double bar z. And then refresh my memory. What does a double bar z stand for? Integers. That's why it's called the greatest integer function. The only thing that's going to shoot out of this, like if you called that y equals round down of x instead of f of x, the only thing that could shoot out, you can put in anything you want to for x, correct? I could put in a decimal, I could put in a negative, I could put in a positive, I could put out a 0. But if your job is to round it down to the nearest integer, what's the only thing that's going to shoot out for a y value? An integer is the only thing that's going to shoot out. If you put a negative 2.2 in there, in the round down brackets, won't negative 3 shoot out of that situation? Isn't the only thing that could come out of it an integer? That's why the range is only going to be some sort of integers.
All right, so as you can see here, we're going to ask to graph a step function right here. You can see it's step because of these double brackets, and it's going to be round down. So the crazy thing is we'll need different intervals to, like in our domain. So here's our x column, here's our y column. Let's make a table of values. And then just kind of trust me on this. Let's do this. It's round down. So like every integer from 0 included all the way up to 1 not included would totally like round down to 0. Like if I asked you pick any number in this range, like pick a half. Isn't 1/2 between 0 and 1? So 1/2 rounded down. That would round down to 0. 7/8 rounded down. 0.9 rounded down. It would go down to 0. If I told you to pick 1, it's like, no, 1 would not round down to 0, so that's why 1 is not included. But every stinking decimal between 0 and 1 will totally round down to 0. So that's why what we'll do is we'll just kind of substitute that in. It's like if I put 0 in here, 0 rounds down to 0. Cool. Now add 1 to it. That would give you 1. If you put 0.5 in here, 0.5, round it down to 0. Excuse me, round it down. It goes down to 0. That would go up to 1 when you add 1 to it. If you put 0.7 in here and round it down, it goes to 0. Add 1. So everything that we're putting in for x in this zone rounds down to 0. Add 1 to it, and you get 1. And let's kind of graph that step real quick. So I'm just going to make a cool little scale here. They want us to label the scale. So on the x-axis, let's just kind of skip every other one and go by halves. So it's like there's 1, there's 2, there's 3. Do that on the negative side, -1, -2, -3. Do that on the y scale too. Just go 1, 2, 3. So we're going every other one, -1, -2, -3. And let's graph this first step right here, because this is a step function from 0 to 1. So on the x-axis scale, we're going from 0 to 1. The y value turned out to be 1. So when x is 0, it's basically like you're graphing this ordered pair here. You're going to graph 0, 1. All right, so I'm going to graph that ordered pair as 0, 1, 0, 1. I can put up here 1, and that's a closed dot because 0 counts, right? It's in the bracket. And then you're going to graph like this ordered pair. You're going to graph 1, 1. So 1, 1 would be right here, and that's an open dot in this situation because the 1 in the x value domain does not count. And there's your step. Everything in between there also gives you a y value of 1 back when you're all said and done. So there's the first step. Now let's do the second step. If we went from 0 to 1, now we're going to go from 1 to 2. 1's going to count. 2's not going to count because everything in this interval rounds down to 1. So that's going to round down to 1. If I picked 1.5 and round it down, it's going to go down to 1. Pick 1.9 and round it down, it's going to go down to 1. So everything in this green interval rounds down to 1. Then if I add 1 to it in this situation, that's going to give me a y value of 2. So I will plot that as two different ordered pairs. So I'm going to plot 1, 2, first off, 1, 2, 1, 2, and that's a closed dot. How do I know that it's a closed dot? Because that's a bracket right there. 1 actually rounds down to 1. Then I'm going to plot 2, 2. 2, 2 is the open dot though. These are like the boundaries of the steps that we're making right here. And everything in between, because this rounded it down to the nearest integer, also rounds down to 1 in this situation. And let's do another one. I'm going to go, so I went from 1 to 2, I'm going to go from 2 to 3. I'm just counting by integers right there. It's like 0 and 1 are integers, 1 and 2 are integers, 2 and 3 are integers. So everything in this purple range right here will round down to 2, because anything in there is like 2.1, 2.2, 2.3, 2.4, etc. It's all going to round down to 2. Then you got to add 1 to it, because that's what this function tells you to do, and you'll get 3. So now I'll plot these endpoints of my step. It'd be at 2, 3, which is a closed dot, and then 3, 3, which is an open dot. And then this pattern is going to continue as you go on, and you can see that your dots line up nice and linear. You're like rising 2 and running 2, rising 2 and running 2. You're really rising 1 and running 1, so we're counting by half. So you can continue this pattern because it's linear, down 2 to the left 2. These are where all my closed dots are going to be, down 2 to the left 2, down 2 to the left 2. And then you can do the same thing with your open dots. You see that they go down 2 to the left 2, down 2 to the left 2, down 2 to the left 2, open dot, down 2 to the left 2, open dot, down 2 to the left 2, open dot, and connect those puppies together. It's a piecewise linear function. It's a step graph, so that's going to continue in this situation. Now let's talk about our domain. The domain, if I did my straight edge test, I start way over here at negative infinity. Remember those steps are there, but I'm going to start over here just so you can kind of see where the steps really are. These steps continue on forever and ever and ever. It's like, is my straight edge touching the steps? Yes, yes, yes. Then I get to this critical point right here where it's like, oh, it's not touching this guy right here, but doesn't start touching this step right here to close dot. So he's still touching. Oh, he's still touching this step right here, still touching. Then all of a sudden I just jump steps, and it's like all the way from left to right. If I went from negative infinity to positive infinity, that straight edge is totally touching the steps. So from negative infinity to positive infinity is what that domain is. Or if you put it in set notation, it's instead of all x, such that x is an element of the real numbers. Like all real numbers work. So either notation. But man, if you want to do the range, which we just kind of talked about here earlier, in the previous couple of minutes ago, like the range, it's like, okay, let's just go where the steps are. Remember, this goes on forever down below, but it's like, oh, there's a part, you know, it's touching the step, and then I slide all the way up. We're only looking at this edge of my straight edge, by the way. And it's like, oh, it's not touching anything, not touching anything, not touching anything. Oh, now it touches. Here at -1 for a y value, and then it's not touching, not touching, then not touching. Now it touches at 0 at a y value, and it's not touching, not touching, not touching, touching at 1. It's only going to touch at the integers. That's totally what this function does, is it rounds down to the nearest integer. So I can't list that in interval notation. It's not possible. So it's the set of all y's such that y is an element of the integers, which that's the double bar z in that situation. Because the only thing that this is going to shoot out for y values is integers.
We need to make a table of values. Okay? We need to make a table of values, so you can just freehand that. But this is where we got to slow down and pay a little bit of attention. Okay? Here's what I want to do. We can make up anything we want to for x, correct? But I need to realize this. I want x to be, let me change colors. Let's just start at -2. Let's say -2 is like the first. I'm just making that up. Who cares? Whatever. -2, right? If I want to start at -2, I want to do this. Copy this down for me. That's what I want to let x equal. Now that's an interval notation, correct? Doesn't that mean that I'm letting x stand for any stinking number from -2 included, right? All the way up to -1, which is not included. Why did I go from -2 to -1? Isn't that an integer of difference, correct? -2, the next integer after that is -1, correct? But I want to include it here and not include it there, and let's realize why. What if I put -2 in for this? What does negative 2 round down to? Negative 2. Take away 2, what would you get? 0. Cool? Let's say I put in negative 2.1. What do we get? My bad. Sorry. I don't know what I was thinking 0 for, but negative 4. Right. My bad. Brain fart. We okay with that? Negative 2, take away 2 is negative 4, right? Sometimes we get confused with absolute value with those. Is that all right? That's what happened to my brain right there. I got absolute value because that's what I taught last hour. Is that okay? So that's negative 4. Now, pick me a number in this range. Isn't negative 1.5 in this range? Would you agree with that? What if I put negative 1.5 in here? What does negative 1.5 round down to? Negative 2. Take away 2 more again. What would you get? Negative 4. Wouldn't you still get that? What if I put negative 1.1 in for x? What would negative 1.1 round down to? Negative 2. And then take away 2 again. Wouldn't you get 4? Any number that you can think of between negative 2 included and 1 not included, any number you can think of, it's going to round down to negative 2. Are you with me on that? So that's why I chose this whole stinking range. Now let's graph that little portion just for fun to start out with. Do we have a scale provided for us on these grids? Yes or no? Yes, the ones on your homework will not. That'll be our first move. We've got to do scales. But let's do this. Isn't x, didn't we say negative 2 counts? Correct? So let's go to negative 2 on the x-axis. It counted, but we've got to go to negative 4 also on the y-axis. You with me? I'm plotting the point negative 2, negative 4. And it counted. Correct? And didn't everything between negative 2 and negative 1 not included also count to give us a negative 4 for this situation? So that means that if we go to negative 1, negative 4, and put an open dot right there, and connect those puppies together, that's what this graph would look like. Any number in the world that you want to, between negative 2 included and 1 not included, would shoot out a y value of negative 4 in that situation. Isn't that what I was substituting in? It's all right if you're a little fuzzy on it. Just hang with me. Okay? Now, here's my next x value that I'm going to choose. I'm going to start at negative 1 and go up to what? 0 not included. Cool? And the moral of the story is, all you got to do is put in your far left number and it will give you the right answer. If we put a negative 1 in here, what does negative 1 round down to? Negative 1. Take away 2 more, what would you get? Negative 3. And if I put in a negative 0.5, negative 0.5 would round down to negative 1, and I take away 2 more, wouldn't I get a negative 3? If I put a negative 0.1 in, I would round it down. All of the numbers between negative 1 and 0 would round down to negative 3 when negative 1 is included and 0 is not included. So let's graph that guy. We go to negative 1, negative 3, and then it goes over to 0, negative 3, open dot, and we connect it. You can just freehand that little guy together usually. You okay with that? What's the next number that I want? I want to use 0 all the way up to what? 1 not included. Now, how do you know which ones to include or which ones to not include? It's like, how did you know this one had to be the bracket and this one had to be the parenthesis? It's all about round down. And isn't this the smaller number, which should be included, and this is the larger number, which will not be included? Is that all right with you? Round down means include the small number and don't include the large number. Okay? So check it out. Where would we go? It would go to what? If we put 0 in, what would we get here? 0 minus 2 is negative 2. You cool with that? And then we plot it. And then it's time to find a pattern. These are linear, my friends. These are linear. Can you pretend that that was in slope-intercept form by thinking of it like this? Y equals, forget that those bars were there for a second, that bracket was there. Wouldn't it look like this? Do you know what the y-intercept is, my friends? What's the y-intercept? Negative 2. Did this cross the y-axis at negative 2? What's the slope of this puppy right here? 1 over 1, correct? Didn't we rise? Whoa, I went up 2 and to the right 2. Well, how much are these going by, really? By halves, right? Didn't I really rise 1, run 1 also? Isn't that what's going on from here? So I do want you to make this table of values. with a few points in it. Cool? And now to finish this off, do you see how all the dots are on the left side? All the dots are on the left side, the closed dots. So let's keep doing that. Let's rise to, run to is basically what this is doing. Rise to, run to. Rise to, run to. And just keep on keeping on until you can't go any further. You with me on those? All right, all I did was put all my left side dots. Now see all these open dots? Check it out. You can still rise to and run to from the open dots. Aren't they following the same slope also? So rise to, run to. Rise to, run to, which is really 1 over 1. Oh, out of spot. That's all right. I'll put it. Then I'm going to connect them all together. Cool? Will this keep going, or does it stop? It keeps going, right? So what you need to do is put dot, dot, dot with a little arrow, saying that thing's going to keep going up that way. Will it keep going down this way also? So dot, dot, dot with a little arrow go this way. It's going to keep on, keep going. It's a linear situation. Wasn't it just like a line, right? This is linear, except it's in pieces. Ba-boom, ba-boom, ba-boom. These little steps. That's why it's called a step function. Does it look like a little staircase to you, if you will? So let's talk about domain and range. Domain is left versus right. Okay? Now this is going to keep on keeping on. You see, if I kind of started, like how far to the left would I be able to go? Well, it's going to keep on keeping on. How far to the left will we go? Negative infinity. And how far to the right will it go? Well, check it out. It's like, here's an open dot, dude. But doesn't this red dot right here fill in that open green dot right there? This was a -1 for a y value, or excuse me, -1 for an x value. Well, doesn't this x value turn out to be -1 right here? Do all the open dots end up getting filled in by those closed dots if you're looking left to right? So what's the domain of every step function according to what it tells you up above there? All real numbers, right? Negative infinity to positive infinity. There's never an x value that will never get filled back in. This closed dot ends up filling in that empty dot when you're just looking from left to right. There's no left and right gaps, if you will. Are there up and down gaps? There's a total gap right here, up and down. I can't fill that in, I can't fill that in, I can't fill that in. But what did the y values turn out to be every single time? What are these numbers? -4, -3, -2, -1. They're integers, correct? So the range will be the set of all y's, such that, what do you want to say after that? Y is an element of the integers, which is that double bar z. Close it up. And you notice that we had to do that in set notation instead of in interval notation, because if you wanted to do it in intervals, you'd be going on forever. You'd be like, oh, it looked like this, from -2 to -1, union, from -1 to union, 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 and it's like, So people are like, how come we don't do it all in interval notation the whole time? Because you can't do it in interval notation the whole time. Well, how come we don't do it in set notation the whole time? Because set notation is ugly when you have to do some things, you know? It's like, it's ugly. So that's why we have two forms of domain and range. Let us go back to number 1 now. Let's make a little table. And this is a round downer, correct? Round down. So let's start. And I'm a fan of, now that we've seen one, of starting at 0 and going to 1. Y'all cool with that? I like 0. 0 is an easy number to deal with. How come I included the one on the left and not the one on the right, though? Round down, right? Round down. We will see some round ups here in a short while, but round down means include this guy. Cool with that? If we put 0 in, what's 0 rounded down? 0, take it times 2. What would you get? Boom! Okay, let's plot it right away. We went to 0, 0, and then it goes over to 1, 0, which is not really included. Right, open dot, closed dot. Little guy. Then what's my next one that I want? 1 all the way up to 2, not included. Sorry, my pen's freaking out. Which one do you substitute in? You substitute in the guy on the left. You put in a 1, what's 1 round down to? 1, take it times 2 and you get a 2. Interesting? I want one more. In your table, I would always like to have 3 of these puppies. Okay? So one more. Oh, sorry, let's graph it first. 1 goes all the way up here, which is included, and 2 not included. So doot. I didn't graph that right at all. My bad. 1, 2. There we go. That would be much better. Is that all right? And then finally, I'll do 2 to 3. That whole interval of x's. I'm letting x be anything in the range from in the domain of 2 to 3, 2 included and 3 not included. So that would shoot out 4, right? And then 2, 4 way up yonder. And it went all the way to 3, right? And now let's do the pattern continuing. Just finish the rest of these off. You can realize that it went 1, 2, 3, 4 spots down and 2 spots to the left. So can't we go 1, 2, 3, 4 spots down and 2 to the left? 1, 2, 3, 4 spots down and 2 to the left, and that's all I'm going to be able to get. Just counting. Down and left, down and left. The slope is 2 over 1. Can you see that from up here? Is rise 4, run 2 of these spots, which is really 2 over 1. Isn't that what the slope of that says right there? What's the y-intercept of this puppy? 0. Isn't that right where it went through? So then we go down and open dot it, open dot it. Domain, it's free. What's the domain for step functions every single time? Negative infinity to positive infinity. I didn't finish my graph though. What didn't I put on my graph? The little doots, continuations. Range, it's not as easy as you think it is. Let's look at what I got in my table so far. 0, 2, 4. Those sure are integers. But is every integer in the world going to come out of this situation? Is every integer in the world going to come out? Will we ever get a 1 to come out? Or a 3? Or a 5? What kind of integers are these turning out to be every single time? Well, can we get a negative 2? Can we get a negative 2 for a y value? Can we get a negative 4? Well, why didn't we get a negative 3? Why didn't we get a negative 1? Why didn't we get a 1? What made them turn out to be all even type of integers? What made them do that? Didn't we take that integer and double it every single time? So integers is not the range. It's more specific than that. Which integers are we talking about? Let's do it out loud. We already said the positive doesn't count. There's some negatives, right? Negative 2 is in there. Negative 4 is in there. Negative 6, negative 8, negative 10, negative 12. What kind of numbers am I listing? Even integers, right? So how in the world can we put that in proper set notation? How can we put even integers? Because if you write this, this says all integers. What do we want to do? Any ideas before I help you with it? How can I make that say even integers? Positive has nothing to do with it. Even is what I want it to be. Positive is different than even, correct? What makes things even? I guess we don't even know that. What makes a number even? This says the set of all y's you want to, just as long as y is an integer, right? Will all y's come out of this? Is that what we get? What needs to get doubled in here? Does this, or this need to get doubled? A, B, or C? And you can't double a set, right? You have to say, you can't double the integers. I know what you're trying to think of, but this has to be something, one of those double bar numbers, either a natural number or an integer or a whole number or all that stuff. Can't double this. So one of these two's got to get doubled. Which one's got to get doubled? A is the right answer. It's the set of all 2y's, right? It's hard to understand. I know that. But it's the set of all 2y's, just as long as, such that y is an element of the integers. It's the set of all 2y's. Because here's what this says. It says, what's y got to be? Y's got to be a what? Y's got to be an integer. Now, what are you doing to it? You're doing what to it? You're doubling it. So what does that mean that they'll turn out to be? They'll turn out to be even numbers. What I'd like you to do underneath this is put this, so you can understand what you did, even integers. Set of all 2y's, such that y is an element of the integers. Now, what would this mean, just for fun, before we move on? What would this mean? What does that mean? Like, what kind of numbers would shoot out of it? Multiples of 3, 6, 9, 12, 15, 18, 21, even -3, -6, -9, right? These are all multiples of 3. As long as y is an integer, boom. Now, how about this? What would that turn out to be? Multiples of what? What number is this in front of y? Would you be comfortable if I wrote it like that instead? Like, isn't that y over 2, which is 1/2 y? So you take an integer, but you divide it by 2 every time, so you can get a half, a 1, a 3/2, a 2, a 5/2, and et cetera, et cetera, et cetera. Okay? Let's go to the back side.
Now here's a weird one, because we've got ourselves a multiplier inside the bar. So let's just kind of see what happens before we really start making our tables. If I go from 0 to 1, like we kind of have been doing right here, let's just see what happens. Everything in this zone, because we're rounding it down, we know it's going to round down to 0. But like, what if I chose, so it's going to round down to 0 in that situation, so obviously there's 0 for this situation. Like if I pick 0.5 and put it in there, it's going to round down to 0. But what if I went from 1 to 2, like we have been doing, we just kind of begin going up by like multiples of 1s in this situation? Like, what if I picked 1.5 and I put it in there? So if I took 1/2, because it's got to get multiplied by a half, 1/2, clear, sorry, 1/2, and I put 1.5 in there for my x value, because that's what I'm trying, a number between 1 and 2, and I actually multiply them together, what do I get? I get 0.75. 0.75, after you round it down, rounds down to 0. And it's like if I did 1.9, isn't 1.9 in this range? So if I did 1.9, and I have to take it times a half, I still get a number less than 1. So like, basically what this is saying right here is this range is like, it's got to be 2 wide. So from 0 all the way up to 2, everything's going to round down to 0 in this situation. We don't want to put this, erase it please. 0 to 2, it's going to give you all the way down to 0. Then your next interval, it's got to start over at 2 again, but it's got to be 2 wide because this has got this divide by 2 in here. You need to get twice as wide as before of what you were. So since you were only 1 wide before, because there was always a 1 in here, now whatever this denominator is, you got to have a range of 2 wide. Everything in there is going to round down to, well, let's find out. Let's just kind of put something in there. Let's put 2.5 in there. My calculator. 2.5 times a half, and let's see what it's going to round down to. That's 1.25. It's going to round down to 1, right? And then if you go from 4 to 6, you got to go 2 wide on your domain because this thing's got that multiplier. It's going to round down to 2. So really, there's some tricky stuff going on with some of these. Let's graph this guy now. On my x scale, look at this. I got to get all the way up to 6. So 1, 2, 3, 4, 5, 6, 7. Let's just go by 1. So 1, 2, 3, 4, etc. Same thing on the negative side. And then on the y, it's only going to count by those 1s. So like we can still go the every other 1 on this guy if you want to. And this just takes a little trial and error to kind of figure out. There's no harm in counting literally by 1s. It's just whatever. I kind of know what this is going to look like already. So just trust me that on the y it's going to go 0, 1, 2, 3, 4. I don't need to get all the way up to 6 or anything like that to make my steps and see this guy. But from 0 to 2, so from 0 to 2, you're going to shoot out a 0. So I'm going to plot 0, 0 as a closed dot, boom, and 2, 0 as an open dot, and there's your step right there. And then from 2 to 4, so 2 is, if you're going to get a y value of 1, so you're going to have your closed dot at 2 and open dot at 1. And then from 4 to 6, it's your closed dot here, open dot there. So there's your step function. That pattern is going to continue, and then just bring it on down. So put all your closed dots down, shoot to the left too. Remember, our scale's different here, so that's why it's going differently for us. And then I'll shoot to the left. Good. Put that as where I put it. Sorry. Down 2 to the left, 2 here, here. And then there's your steps. So what's going to kind of change on this is just the scale. These steps are really twice as wide as before. So the domain is a set of all x's such that x is an element of the reals, or you can put it in interval notation from negative infinity to positive infinity. But the range, you can't put it in interval notation because you're only getting back integers in this situation. So that's your double bar.
Those were round downs. And in real life, round downs don't happen that often. Think back to your geometry problems that we did when you had to go buy gallons of paint at the store, and it's like, how many gallons of paint would you need to cover the room? And you figure out you need 3.8 gallons of paint. Would you round that down to 3 gallons of paint? Is that what you go by what would you buy at the hardware store? You got to round it up, correct? You're going to order concrete, and you need to order 2.8 cubic yards of concrete. So what do you really order? You order 3 cubic yards. You got to round it up. Round up is a way more of a real-life situation. So one psychologist charges for counseling sessions at a rate of $85 per hour or any fraction thereof. Any fraction thereof is a very, very, very real-life problem. Let's say you go to the psychologist for an hour and a half. Right? It's not a nice, neat integer. 1.5 hours. How many hours do they charge you for being there if you were there for an hour and a half? Round it up, 2 hours. Let's say you're there for an hour and 5 minutes. How many hours do they charge you? 2. They're going to round you up. Cell phone problems. How many minutes do you use? Well, I was on the phone, my minutes that I used, I was on the phone for 2.5 hours. What did they really charge you for? Or 2.5 minutes. So 2.5 minutes. I was on the phone for 2.5 minutes. What did they really charge you for? 3 minutes, because it's any fraction thereof. They're going to round you up. So that's what that any fraction thereof means. Draw a graph to represent this situation. First thing we need is a title on this graph. Get me a title with PAL. It's just got to describe the situation. Here's my title. Price of counseling sessions. Some of you did per hour. Some of you, it doesn't have to be exact, but that's what it's about. Isn't it about the price of counseling sessions? Now we got an x-axis and we got a y-axis. We got to figure out which one's in our domain and which one's in our range. Which one is independent and which one is dependent. What goes on the x-axis? Well, first of all, let's figure out our 2 labels. What are we talking about here? It's all right here. Boom, boom. Dollars per hour. Dollars per hour. Do you know how slope works? What's slope? Is it y is on top and x is on bottom, or x is on the bottom or top and y is on the bottom? Which one's on top in a slope situation? This is dollars per hour, correct? Which one of those is x? The one on the bottom, right? Hours, correct? So hours goes down there. And what do you want to do? Do we need to label every single one of these thinking guys? Do you want to make a graph that small and scrunched, or can we spread it out a little bit and get the gist of it? So we definitely will start with 0 hours, and then what do you want to go by? Well, I'm just saying, how many spots do you want to skip to get over to 1 hour is what I'm saying. Definitely wouldn't do 3, personally, right? Because 3 puts us into a weird gap, because then each one of those represents 20 minutes apart, right? You can go by 2s. Wouldn't that be like a half an hour, then a whole hour, then another half an hour? If you went by 3s, we don't really talk in 20-minute increments. You can go by 4s, though. Can we talk about like a quarter of an hour, like 15 minutes, half an hour, 45 minutes? Doesn't that make more sense? So here's what I went by. Boom. I went every other one. I went by 30 minutes, if you will. Okay? And then on the y-axis, what would our label be over here? You got to have these labels, guys. These are all points. If you do a real, what would we do over here? The price in what? Dollars, right? Because there's other things. You could do it in euros. You could do it in pesos, whatever. The price in dollars. And now it's the interesting thing. What would you like to go by? I want to go by 85 since that's our slope, but I'm not going to do it every single spot. I'm again going to go every other one right there, just to spread it out a little bit. We will never go into those ranges of 42.50 is what we're really going by. We're going by $42.50 each time, but we're never going to get into that zone. Cool? So get that all nice and made, and we'll make a little table here. What's the number you want to start with right here? 0 to 1 hour. Remember, x is hours. What if you were in there from 0 to 1 hours? But which one is included and which one is not included if this is a round up situation? Give me the included one, the one on the right. This guy is not included. You with me on that? Now let's stop right there and figure out what it would be. What if you were in there for 0 hours? How much would they charge you? Nothing. You didn't even go to the psychiatrist. Why should they charge you anything? You with me on that? But what if you were in there for 1 hour? What would they charge you? 85 bucks. So you have to put the number in that's included. You with me? What if you were in there for a half an hour? How much would they have charged you? 85 bucks. Isn't a half in this range, in this domain, if you will, right? But zero's not going to count because if you were in there for 0 hours, that means you never even went in the first place. You pay $0. Let's graph that. Open dot right here, close dot, oh sorry, it's at 85, my bad. Open dot right here, close dot at 1, meaning you pay nothing if you went for 0 hours, but any little fraction between 0 not included and 1 included, you're going to pay 85 bucks. Cool? One more. Next guy. Not included 1 to 2 included. How much would that turn out to be? 170 bucks. And that's all I need to finish this graph off. That means at 1 hour, this didn't count because aren't you still at the $85 range? You were only in there for 1 hour. But if you went anything above an hour, you're going to get paid. You have to pay $170 for that situation. Then count it up. So rise 2, rise 2, rise 2, 2. Open dots. Let's do these first. Bow, 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 bow. Bow, 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 bow. Bow, 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 bow. Bow, 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 bow. Chicka-pow, 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 chicka-pow. Notice which dots are filled in and which dots are open if it's round up. Round up is the dots on the right are filled in. Round down, the dots on the left are filled in situations. Cool?